There are 7 questions, each with a reward of $1 million for solving them. These 7 questions are known as the Millennium Problems, set by the Clay Maths Institute in the year 2000. Since they were created, only one of the 7 problems has actually been completed, done in 2003. Today we are going to go into detail about 2 of these problems to find out why they're so interesting. The first problem is known as P versus NP, and is actually more in the realm of computer science than mathematics. To understand this problem, let's start by establishing what P and NP stand for. P stands for polynomial time, which for all intensive purposes just means it's easily solvable in a reasonable amount of time. Mathematically, it means that if there are n items to be dealt with in the problem, then it would take n to some power operations to solve it, which for computers this is easily doable. An example of this would be something like sorting a list of names into alphabetical order using a bubble sort. To perform a bubble sort, you look at the first 2 items and compare them. If the first item should appear after the second item, then they swap. If not, then they will remain the same. Then repeat this process for every item in the list. In order for the list to fully be solved, you must do this another n times. This means it would require n squared operations to solve the problem. The NP stands for non-deterministic polynomial time. This means you can verify if a solution is correct in polynomial time. However, it's important to note that finding the solution to these problems requires exponential time to solve. So even for a computer, it would take an unreasonable amount of time to solve. Mathematically, exponential time means you raise some number to the power of n, which means the problem grows incredibly large even with only a few items. An example of this is the traveling salesman problem. This is where you have some number of points that you have to deliver to, and you have to find the shortest possible route between them. The problem with solving this is to verify you have the correct solution, you have to go through every single route. Let's say you have 50 points. That means you have 50 to choose from to start with, then from each of those you have 49 to go to. Following this logic, you can see that there would be 50 factorial routes. To understand how large that number is, if we round it, that would be a number with 64 zeros. However, if you give me a particular route and tell me how long it is, it's very easy to verify how long that route is. So now onto the crux of the problem. Are all NP problems really just P problems that we haven't found the right solution to yet? Most mathematicians believe that P does not equal NP, which would mean that some problems have a built-in limit to how quickly they can be solved. However, if P really did equal NP, then there must be some very positive and also some very negative ramifications. For instance, it would mean that no password is safe and could be solved in a reasonable amount of time. On the other hand, we'd be able to do lots of incredible things, like solving disease and perfectly predicting weather patterns. Now let's talk about the second problem, Riemann's hypothesis. Riemann's hypothesis proposes that all non-trivial zeros of the Riemann zeta function lie on a specific vertical line in the complex plane where the real part is 1/2. So let's break down what that actually means. The zeta function has 2 main forms. There's the standard form, which works for positive real numbers, and the functional form, which works for both negative and complex numbers. The standard form looks like this. Zeta of s equals 1 plus 1 over 2 to the power of s plus 1 over 3 to the power of s plus 1 over 4 to the power of s, and it continues just like that. Let's use s is equal to 2 as an example. As you can see, if we keep adding up the individual terms, they start converging to a number. What is that number? It turns out that number is exactly pi squared over 6, which is a pretty interesting result. Now the functional form is much more complicated, and it is as follows. Zeta of s is equal to 2 to the power of s times pi to the power of s minus 1 times sine of pi s over 2 times gamma of 1 minus s times zeta of 1 minus s. Okay, so now that we've established what both of the forms are, let's try to understand the actual problem. We are trying to look for all of the special cases where zeta of s is equal to 0. There are an infinite number of trivial cases, and all these trivial cases follow the pattern of being a multiple of minus 2. This is because in the functional equation, the sine part will always be equal to 0. So what are the non-trivial cases? Well, they all follow a very strange pattern. All of them are complex numbers where the real part is equal to 1/2. So far, supercomputers have checked over 10 trillion non-trivial zero cases, and all of them fit this pattern. One fascinating feature of this is that the imaginary part of the number matches exactly onto the energy levels of heavy atoms like uranium, which is a very curious property for it to have. So tell me what you thought of these problems in the comments below, and let me know if you want me to try and explain any of the other problems. If you enjoyed, consider leaving a like and subscribing, it would be greatly appreciated. That's all for today. Thank you for listening, and goodbye.